And I'm very happy to welcome today Xu Han for our international workshop on interval methods in control. And Xu received her PhD degree from INSA Toulouse in France in 2021. And she's currently a postdoctoral researcher at the Université de Caen, Normandie, again in France. And she's especially working on observer-based fault diagnosis and fault-tolerant control of nonlinear dynamic systems. And we're looking forward to your presentation on the observer design for a class of nonlinear uncertain systems with sampled outputs, with, I think, a quite timely contribution, an application area in the domain of heat reaction estimation for chemical reactors. Now, Xu, we're looking forward to your talk. The floor is yours.
Okay, thank you, Andrea, and hello, everyone. I'm very happy to be here and do a presentation. And my presentation will focus on the observer design procedure for the nonlinear system with sampled outputs. And in the end, I will give an application for the observer design to estimate the reaction heat in chemical reactors. And here, in my talk, I will talk about the observer design, two kinds of observer design. First is the standard high gain observer design for the system with sampled output. And the second, I will present an improved non-picking high gain observer design process. And then I will give the simulation results and the conclusion. So we will start from the standard high gain observer design. And first of all, we consider a class of general nonlinear system with the following triangular form. And here the X is the state vector, and the phi is the nonlinear function, and the matrix A, B, C has the form presented here. And then pay attention that the output Y is only available at some sampling instant. And this sampling instant, we called it Tk. And so the epsilon T and omega T are system uncertainties and the output noise. And in the following, we will define the Ts as the sampling interval. And we assume that all the state is bounded and the function phi is Lipschitz, and also the function epsilon and the noise signal omega is also bounded. And they have a super essential upper bound, it called delta epsilon and delta omega. And what we want to do is to design a continuous discrete time observer. And then we can give a continuous time estimation of the state, and by using the sampled measurements, YTK. So based on the continuous time high gain observer designed in the reference, then we proposed a kind of discrete continuous time observer. And here, the equation 2 is the basic form of the observer. And here the X height is the estimated state, and the K is the observer gain vector. And it should be chosen that the A bar equal to A minus KC is Horowitz. And the matrix delta theta is a diagonal matrix with the following form. Here the theta we suppose is bigger or equal to 1. So for the considered observer, we can have this theorem. That means for any bounded input U, we can have the observation error X height minus X. It is exponentially converged to 0, or a very small value here. And in the following, I will give the proof of this theorem. And before that, I want to introduce a lemma which will be used for the proof of the convergence. And here, this lemma is used to solve the differential inequality presented here. And we can see that for the differential inequality, we can have the solution in this form, and the proof of this lemma can be found in the reference. So I will not introduce too much here. And then we will begin our proof for the convergence. And first of all, we define the observation error system. It is named as x tilde. It equals to x height minus x. So it's a very general form. And we can easily calculate the derivative of the x tilde. And then here, the phi is the difference between these two functions, phi ux hat and the phi ux. And first of all, we will do a coordinate transformation, and we set the x bar equal to delta theta times x tilde. And by using the diagonal form of the delta theta, and we can easily have the following identity. That means the delta theta times A times delta theta super minus 1, then it equals to theta times A. And also for the matrix C, they have this the identity like this. Then we can do the transformation and get the derivative of the x bar, and it is presented in the equation 1. So here, after the transformation, we will add and subtract one item, the theta k c x bar, and then we can rewrite the derivative of the x bar in the form of equation 2. Here, the a bar is a minus kc, and the function z is short for the cx bar minus this part. And pay attention that in the following proof, I ignore the continuous time representation t, and I will keep the tk to represent the sample time, the sampled instant. So we will define a Lyapunov function Vx bar, and it equals to x bar transition times p times x bar. And the p is the symmetric positive definite matrix defined before. And we can easily calculate the derivative of the Vx bar. And then, according to the Lipschitz assumption mentioned before, and the triangular form of the function phi, for any theta bigger than 1, then we can have this part is less than this one, this item, this term. And the third part is less than this one. And also the last part, we can also find its limitation, upper bound. And then we can combine all this inequality with the derivative of v, then we write the derivative of v like the equation 4. And here, we can see that the derivative of v is an equation about square v and the equation of the norm of x bar. And in the next step, we will take a theta which is large enough, then we can easily, we can simplify the derivative of v, like the equation 5. And here we can see we have 1, 2, 3 parts for the derivative of v. And we can see that for the norm of z, which one? The z is defined as before. We don't know its upper bound. So how to calculate the upper bound? And I will introduce this in the next step. Here for the calculation of the norm of z. And we already defined the function z is short for this function. And here the x x bar 1 is the first element of the vector x bar. And here we can calculate the derivative of z. And here we also define a function called phi1. And then we will integrating the equation 6 from tk to t. And we can easily find that the ztk equals to 0. So we can have the following expression, like the equation 7. And here, by using the Lipschitz assumption of the function phi, we can rewrite the norm of z in this form. Here, we transform this part as a function of the norm of x bar. And here, it's easy to find that the norm of one element is less or equal than the norm of the whole vector x bar. So we can rewrite, we can get the norm of function z. So here, by using the upper bound of function z, we can have the derivative of v as a function of vx bar or a function of square vx bar. So we can also have the equation like 10. We calculate the derivative of the square function of vx bar, and we can easily find that this derivative is a function of the square v. We can see here. And here we define the sigma as the square lambda capital M by lambda small m. So the lambda capital M and the lambda small m is the condition number, is the eigenvalue, the maximum and the minimum eigenvalue of the matrix P. So here, by using the lemma presented before, we can solve the differential inequality, and we can go to the solution of the equation 11. And here, the eta theta and the c theta is the function defined here. And then we can obtain the norm of x bar is less or equal than this whole term. So we replace the square vx bar in equation 11, so we can get the norm of x bar. And then we will go back to the original coordinate of the observation error x tilde. So there is a small technique here. We use this function, the 1 by theta super n minus 1 times the norm of x tilde. And it is easy to find that is less or equal less than the norm of delta theta times x tilde. And the delta theta times x tilde equal to x bar. So we can get the limitation of the norm of x tilde. So here we can substitute the parameter c theta defined before, and we can get this final result. And it means that our observation error will converge exponentially to 0, or very small value. So that is the proof of the presented theorem. So it is also the convergence of our observer. And we can see that when the TIs is very small, that means the sampling interval is tends to 0. And we can see that the E super minor eta theta times T will converge to a constant, and the function n theta will also converge to a constant. So when we don't consider the uncertainties and the measurement noise, the observation error will converge to 0 without doubt. So when we consider the uncertainties of the system, we can also make our estimation error very, very small by choosing a very big theta. Because when we choose a big theta, this item will converge to 0. And so that, but at the same time, the very big theta here, it will cause the peaking phenomenon of the estimation error. So that means the estimation error will become very big at the first time, so during the transition period. So what we wanted is to eliminate this peaking phenomenon. So how to do this? And finally, we find a solution, that is to use a saturation function to saturate this part. And I will introduce the improved non-peaking high-gain observer design process in the following parts. So here, the equation 12 gives the general form of the non-peaking high-gain observer. And this observer design is based on the continuous time observer design. And in this reference, so I will give more explanations. Here, the HT is the correction items, and it is a vector of H1 and Hn. And here, for each H, for each element of H, it is a saturation function like this. For H1, it equals to sat nu 1, and we use the theta super minus eta times K1. K1 is the first element of the observer gain. And with this correction item, and also we use the sampled output. And also for the following HIT, for I bigger than 2, and we can also use a saturation. So that means we will limit our correction item into an interval. So that means once the correction item is bigger than this interval, it will be limited to our correction interval. So here is the basic idea of the non-peaking high-gain observer. And for the improvements of high-gain observer, I didn't finish it, but I will finish this in the future, in the next few weeks. And I will present some results first. So here comes the simulation part. And what we use is a chemical reactor. And here, it has one main reaction. And at the same time, it has 3 sub-reactions. That is the decomposition of the H2O2 and also this reactant. So here the equation 15 gives the mathematical model of the reactor and the considered chemical reaction. Here the C represents the concentration and the T represents the temperature, and the R represents the reaction rate. The QR is the reaction heat, and that is what we want to estimate. And the Q loss is the heat loss in the reactor, and in our case, we consider it equals to 0. And the subscript R and G are the reactions and the jacket of the reactor, and the temperature of the reactor Tg is a constant in our case. And for the others, rho V Cp represents the density, volume, and the specific heat, and they are considered as constant. The UA are the heat transfer coefficient. So here, the calculation of reaction rate can be found in this reference, but we will not introduce them here because what we wanted is to use the sampled temperature to estimate the reaction heat QR. And here we will validate our reactor model. And the orange line is the model we built. And the black dot is the experimental data. And the experimental data comes from our college in the Laboratoire de sécurité des procédés chimiques in Caen, France. And here we also give the initial conditions. And we can see that after 4,000 seconds, there is a big difference between the model and the experimental data. So it's normally because we use some simplification in the modeling part. And for the exothermic reaction, what we will focus is the dynamic of the reaction. So we will focus from time 0 to 3,600 seconds. That means we will focus on this part. And here, how to estimate the reaction heat. And we will define the state 1, x1, equals to the temperature of reaction TR. And here, for the state x2, we will consider the QR by rho VCP as the uncertainty or the unknown function of the system. So for the rest nonlinear function, we will all put them in the function of phi 1. So we can construct our observer. Here, the equation 17 gives the standard observer design. And for the improved non-peaking observer design is given in the equation 18. And here, the H1 and H2 are the correction item of the observer. So here is the initial value of our observer. And we can see one difference is the difference in the temperature of reactor of the observer. That because we want to see the convergence of the observer, so we make a little bit difference for the temperature. And here I will present the results in two different ways. First, I will present the results coming from our model, and then I will give a comparison by using the experimental data. Here, the first figure, it represents the temperature and its estimation TR hat based on the model we construct. Here, the star, black star, it represents the sampled output coming from the model, and the red line represents the estimated temperature from the standard Hagen observer, and the blue line represents the estimated temperature coming from the non-peaking observer. So we focus on this. We can see that for the standard observer, there is a peaking phenomenon in the at about 2 seconds, and then it will converge to the sampled temperature. But we can see the blue line, which comes from the non-peaking observer. The peaking phenomenon is eliminated by our observer, and in the end, it can also converge to the real temperature. And next, I will give the estimation of the reaction heat. Here also the black line represents the reaction heat coming from the reactor model, and the red line represents the estimated reaction heat from the standard observer. And the blue line represents the estimated reaction heat coming from the non-peaking observer. So when we focus on this, we can see that the red line, which represents the Q height R from the standard observer, it has a bigger peaking phenomenon. And in the contrast, the blue line, the estimation, comes from the non-peaking observer. There is no peaking phenomenon, and they can all both converge to the estimation, to the reaction heat coming from our model. So that means our observer works, and the non-peaking observer can well eliminate the peaking phenomenon. And then in the next case, we will try to use a larger sample interval. So this time we will use the TS equal to 4 seconds, and the results also based on the model we built here. And here is a small focus for the temperature, and both of the observer can converge to the real temperature TR. And it is easy to see that the blue line, the temperature estimated by the non-peaking observer, eliminate the peaking phenomenon. So the observer works very well, and the non-peaking observer can eliminate the peaking phenomenon. So here we focus on the reaction heat estimation, and both of these observers will converge to the reaction heat from the model. And similar as before, the non-peaking observer gives a better estimation results because it doesn't have the peaking phenomenon. So next, I will present the results coming from the experimental data. And in this case, the black star represents the temperature coming from the experiments. And the sampling interval is equal to 2 seconds. And also we use the same color, the red, to represent the estimation state coming from the standard observer, and the blue represents the estimated state coming from the non-peaking observer. So they can all converge to the experimental temperature. And when we focus on this, they have the similar results like those used by the model. And we can see that they all the estimation obtained by the observer, they can all converge to the temperature coming from our experimental data. And at the same time, the non-peaking observer gives a better estimation because it doesn't have the peaking phenomenon for the temperature estimation. So we will come to the estimation of reaction heat. And here we only have 2 colors because unfortunately we cannot estimate the reaction, we cannot get the reaction heat in the real experiments. But we have proved that the observer can well estimate the reaction heat for the model. So theoretically, it can also give a correct estimation of the reaction heat by using the experimental data. So here we focus, we can see they all converge to the same after about 40 seconds, and the non-peaking observer doesn't have the peaking phenomenon. So next, we will enlarge our sampling interval. In this case, the TS is equal to 4 seconds. And for the temperature, both observers can give the estimation of temperature, and they all converge to the experimental data TR. And the non-peaking observer can give a better estimation because it doesn't have the peaking phenomenon. And for the reaction heat estimation, we can see here, it takes longer time for the estimation because our sampling interval is enlarged to 4 seconds. But finally, both of the observer can give a good estimation of the reaction heat. And the blue line, it doesn't have the peaking phenomenon. So that is all of the results by using the presented observer. And I will give a small conclusion. So in my talk, 2 kinds of observer have been proposed for the system with sampled measurements. And one application to estimate the reaction heat has also been presented. And but according to the simulation results, we can see that the observer can both well estimate the reaction heat and at the same time, the non-peaking high-gain observer has a better estimation performance because it doesn't have the peaking phenomenon. And also we can enlarge the sampling interval from 2 seconds or to 4 seconds. So we decrease our work for the sampling. And that is the list of reference disappeared in my presentation. And that is all of my talk. Thank you. So if you have any questions.
Yes, many thanks for your interesting presentation. And yes, I'll just hand over your very last question. If anyone has questions, please feel free to ask them. Carlos.
Hi there, and thank you for a really nice talk. I really like it. And I wasn't completely sure about some things. So could you go to the slide 4, just at the beginning? It's just
yes. Here.
Yes. In this case, we are talking about a hybrid system, right? Because you have a continuous time in the first equation of x prime.
Yes.
But you don't have always an output, right? This output is only going to come time to time. So yes. If we move to the next slide.
Yes.
I think, okay, I think it was on this one.
Continue.
Where we showed the framework. Yes. I mean, you consider the output in the estimation always.
Yes,
so what happened in those times? I mean, what is the time when you don't have an output? I mean, what is TK? What happened with this relation? Because actually you don't have an output in some times, some periods. So what is happening? What are you gonna do in those cases?
Yeah, okay. I understand your question. And here we can see the equation 2. Here is the basic form of the observer. We can see the correction item here for the estimation error, the Cx height Tk minus Ytk. Here we use the sampled output, yes. And before that, for the continuum time t, which located in the interval tk to tk plus 1, we will use for the output part. We will use the output of tk. So that means during this time interval, we will use the output of this time instant tk, and we will have this E super 2 minus theta k1 times t minus tk for this small correction item to make our observer to be a continuous observer, to that it can give a continuous estimation of the states. But for the output, we will always use the output from the sampled instant.
Okay, wait. Let's make an example. Let's assume tk is 0.
Yes.
Right? We are now in 0.3.
Okay.
Right? What is going to happen? And I'm going to take the last output that I took it to correct the system. And what about this e to the exponential to the t minus tk?
Yes. So as you assume, if the tk equals to 0 and for the at time 0.3 seconds for the correction item, what we can get is the measurements from tk equal to 0. So this part will equal, the tk will equal to 0, and the output is the output from time instant 0. So that is no doubt for this. But for this item, the t equals to 0.3 and the tk equals to 0. So that means the output, we will always use the sampled output, but actually the time is continuous. We have a little bit, how to say, maybe a little bit of delay for the time instant. Yeah.
I got it. Mm-hmm. Okay. Okay, thanks a lot. And if we go to the 12th,
yes,
the 12th slide.
Yes, here.
Okay. Yes. Could you tell me a little bit more about this this observer, because I couldn't understand it completely, and I said, okay.
Actually, because the system we considered is a triangular, it's a system with triangular form. So what we have, the output is always the first element of the states. So the y equals to x1. So here, the h is the correction item. And here we use a saturation function to limit this correction item into an interval. So we can see for this H1 equation, so it has an item from the estimation, it's the
last error that they take.
Yes, the last error coming from the sampled measurements. And here, this part is the same as the as the standard one. But here, what we use is the saturation function. So as I presented before in the estimation error, the norm of estimation error, the first part, the big theta, will cause a peaking phenomenon. So we will use an interval to limit this peaking. So that means if the peaking go out of this interval, we will limit it here. So it will not go out of this. So that is the basic idea for this non-peaking of the.
And how do you define this in the equation 14, the beta or the nu? I don't know what's the letter. Yes.
Yes, actually this
it's a positive constant, but okay, how do you define it?
For rational, we use a trial and error method to find the constant.
Okay, that's quite nice. Thank you for a really nice talk.
Thank you for your question.
Okay, do we have any further questions? Okay, I do not see any question at the moment in the audience. Maybe let me ask two questions. The question that just came to my mind when you just answered to the last question of Carlos is, you said you always have x1 as the system output. Is this only a scalar output always, or is it a subvector of the original state vector?
So, okay, we can see the system here. So the output y is always the first element.
Is this only a scalar first element?
Yes.
I was wondering if you could generalize the approach then to a vector valued output that you have, for example, let's say two measured outputs like x1 and x2. Is there a generalization possible that works in the same way?
Yes, actually we can do this. And in the reference in 2015, and we actually consider we have multiple output. But to explain clearly the convergence and all the procedure, I use only the one element. So actually it works for the multiple output case.
Okay, and my second question that I have is, did you check, because typically in such, let's say, chemical reactions, one of the biggest problems is the parameter identification. There are lots of parameters that are hard to identify and not always very robust to be identified. Did you check the performance and the sensitivity of your approach with respect to some parameter deviations?
I don't understand. So you mean we can also use some identification method to estimate the parameters, or?
No. Typically, you're estimating those parameters, or you're identifying the parameters in advance.
Yes.
And what I think what you did in your simulation is you assumed that the parameters in the simulation model and the parameters in your observer, they were more or less identical, or they were maybe even exactly identical. And yes, in your real life experiment, this wasn't the case. In the real life experiment, you have some deviations due to, like we have seen in this open loop simulation that you had. And my question is, did you check in the experiment, which in the simulation part, I think, did you check which of the parameters is the most crucial one to be identified in a reliable way in order to get good performance of the observer? Because this could give some hint on, yes, on the necessity for suitable parameter identification in advance.
Yes, a good question, but in my mind, in my opinion, so for a chemical reaction, what we can get is very easy. We can easily get the temperature of the reaction. And also we can also get the concentration, but the concentration is not as much easier as the temperature. So for me, I think the temperature is the most important, and that's what we can get directly. So that's why here we want to estimate the reaction heat by only using the temperature, because the reaction heat is difficult to estimate. It is a function of the reaction speed, and the temperature is very complex function. So we use the easiest way the observer to estimate the state we don't know. So maybe I think for me the most important is the temperature, and for other state I don't it's not easy to obtain, compared to the temperature.
Okay, thanks a lot. And do we have any further question here in the audience? I think this doesn't seem to be the case. Then, yes, I will be glad also to put your slides on the webpage and that everyone can have a look afterwards at the list of references, especially at the reference I'm interested in, what you said, where you have also the multiple outputs.
Yes, this is the reference too. Yeah.
Okay, that means I'll definitely have a look at this Automatica paper. And yes, now let's check again if there's anyone else who wants to ask a question. So if no, then many thanks again for your presentation. Many thanks for answering all the questions. And to all of you, have a nice Friday afternoon. Have a nice weekend, and see you soon on Friday in 2 weeks for our next presentation here in this seminar.
Okay, thank you. And if you have any question, you can send me an email. You can,